Today, we begin our journey through space, from what is closest to us on Earth to what is most distant from us in the universe. Today's topic is on the Sun, Earth, and Moon, eclipses, why Earth is rare, and the Anthropic cosmological principle. Because the Sun, Earth, and Moon are so close to home, we know a lot about them, and we won't be discussing everything, but there's still plenty to learn. Using radiometric dating, we think that the Earth is about 4.54 billion years old. So how does this work? We have craters that are the result of meteorite impacts. We can look at the samples of those meteorites and analyze their composition. We compare the numbers of isotopes, which are atoms with a different number of neutrons. We compare numbers of isotopes to determine how long that sample has been just sitting there and with some isotopes decaying. We get a half-life, and by statistics, we use knowledge of that half-life, that time it takes for half of those atoms to decay into a different isotope, in order to determine how long ago that sample is a remnant of. So if the meteorite is determined to be about 4.54 billion years old, then that's probably the age of the Earth as well, and of many objects in our solar system. As our solar system formed, the sun became a star, developed a protoplanetary disk, then debris in the disk eventually coalesced into planets. This estimated age of the Earth is also consistent with some of the oldest Earth and Moon samples. Earth's orbit around the sun seems pretty constant, but over large periods of time, there are different cycles it goes through. These are called Milankovitch cycles, named after the Serbian astronomer Milutin Milankovic, who in the early 1900s realized that these were important for predicting the ice ages and for understanding them. The three Milankovitch cycles are Earth's obliquity, Earth's eccentricity, and Earth's precession, also known as the precession of the equinoxes. The obliquity is Earth's tilt. We say that we're at 23.5 degrees. Well, that's what we're at today, but that value varies over time. It goes between about 21 and 24.5. And it takes about 41,000 years to cycle through those values for one period of obliquity. Earth's obliquity is shown here in this top plot and how that changes over time. The second shows its eccentricity and how that goes through different cycles on a scale of about 100,000 years. Its eccentricity, you could think of it as like flexing a little bit. The shape of that ellipse changes a little bit over time. And then this third one is showing the sign of the precession angle. Earth's precession, or precession of the equinoxes, is how its axis is actually rotating over time, about 21 to 26,000 years, somewhere in there. That was realized by Hipparchus, the ancient Greek. To make more sense of precession for the amount of sunlight we receive, we multiply that sign of the precession angle by the eccentricity in order to get this fourth plot, which informs us a lot more about this next one, which is the insolation, or the flux from the sun. How much sunlight does each square meter on Earth get? And this is specifically at 65 degrees north latitude. That is a latitude that Milutin Milankovic realized is important on Earth for the ice ages, because there's a lot of land in the northern hemisphere at 65 degrees north, that when it's receiving less sunlight is easy to ice over. That picture on the right shows an artist's depiction of glaciers creeping down south from the North Pole during an ice age. These bottom two plots are showing a consequence of the Milankovitch cycles and proof that we have had ice ages in the past. It shows oxygen isotope fractionation that we've recovered from bottom of the sea or from Antarctica, from getting a large cylinder of ice. Kind of how you can look at a tree and count the rings to determine how old that tree is. In a similar way, we can look at that ice and how it has built up over the millennia and look at each layer and the composition of that layer to determine how much oxygen there was in the atmosphere compared to other times in history. And that depends on whether Earth was experiencing an ice age or not. So we realized that Earth goes through an ice age about every 100,000 years. It's been doing this for the past 800,000 years. Before that, however, there were ice ages about every 41,000 years, in step with the obliquity cycle. So obliquity is important, Earth's axial tilt, for ice ages, but then something happened about 800,000 years ago. There are different models trying to figure out what that was exactly. Could be a combination of things, both astronomical and geological. But now, ice ages are happening about every 100,000 years. It's probably not just because of the eccentricity. We think that's a coincidence, though it may have a small part to play in this. It is one of the Milankovitch cycles, after all. So we may be heading towards another ice age. The buildup towards ice ages is slow, but emergence from a glacial maximum, the maximum peak of the ice age, is fast because the ice melts fast. We see this during the year, those of us who are north enough to have snow, how it takes time for the snow to settle, to get into that winter. But then in the spring, when the sun's out, the snow can melt pretty fast. There's evidence that the last glacial maximum was about 20,000 to 25,000 years ago. So we're in an interglacial period right now. We should be heading towards a new ice age, but it could take centuries or millennia. And also, with the increase in carbon dioxide in our atmosphere, that could change things a bit. We don't know the future, but Earth is still the best place for life in our solar system. The moon probably formed around the same time as the Earth, and probably from reaccreted material from a collision with proto-Earth. On the side that is facing us, we see darker regions on the moon. These are maria, the Latin word for seas. They don't actually have water today, but they're darker because they were ancient lava flows. On the moon, on this slide, the Apollo landing sites are marked. These are the different places that we have landed on the moon. The first crewed mission to land on the moon was Apollo 11. It landed right there. Apollo 12, Apollo 13 did not land on the moon. They ended up going around the moon and coming back to Earth because there were technical difficulties. They survived. Apollo 14, Apollo 15, Apollo 16, and Apollo 17. Notice they're all on the near side of the moon so that we could have direct communication with them from Earth. We have sent spacecraft also to take pictures of the far side of the moon, and it looks pretty different. It doesn't have all these maria that the near side has, so that's pretty interesting. And we can take pictures of the far side of the moon. It is not a permanent dark side of the moon. That's a common expression. But there's always some part of the moon that is dark, some part that is light. We always have one side facing us because the moon is tidally locked to the Earth. One spin on the moon coincides with one orbit of the moon around Earth. So it is spinning, but it's spinning with the same period as it's rotating. So it's in a one-to-one spin-orbit resonance. The presence of such a large moon actually helps stabilize Earth's axis. It keeps its obliquity from varying too much and too little, which could have drastic effects on Earth's seasons over time. There's also an angular momentum transfer going on between the Earth and the moon. Due to the moon's tides, it is slowing down the Earth's rotation. And as it's slowing down the Earth's rotation, the Earth is transferring angular momentum to the moon, which results in the moon getting further away from Earth. This is a slow process and not noticeable during a human lifespan, but over centuries and millennia, it can make a difference. Eventually, perhaps millions or maybe even a few billions of years from now, if nothing drastic happens sooner, the Earth will also be locked in a resonance with the moon, so that the same side of Earth will face the same side of the moon. That is how the Pluto-Charon system is today. It is totally tidally despun. When that happens, the moon will be a lot further out. So the day won't be about 29 and a half days long. It would rather be somewhere between 50 and 100 of our current days long. There's no other planet in our solar system that has eclipses like the Earth. Most of the other moons in our solar system are not approximately the same size as the sun as viewed from those planets. And even ones that are potato-shaped and move too quickly for a great experience of an eclipse that we have on Earth. One type of an eclipse is a lunar eclipse. This happens when the Earth is between the sun and the moon, and the Earth's shadow falls on the moon. Lunar eclipses can thus only occur at full moon, and they can be observed from anywhere on Earth where it's nighttime. During a lunar eclipse, the moon can appear red, and that is because the only light reaching the moon is light that is going around the Earth through the atmosphere. And so the blue light scatters in the atmosphere preferentially, but the red light can continue and illuminate the moon. As you may guess, this takes place over the course of a few hours. You might hear also of a penumbral lunar eclipse, and that's when the main part of Earth's shadow misses the moon, but just sort of that outskirt shadow is hitting the moon. And you won't get as dramatic of a lunar eclipse in that situation. Solar eclipses are more spectacular. They happen just as often as lunar eclipses, but they're only visible from a small part of the Earth. And that's why they seem more rare. A total solar eclipse can only last for a few minutes, though the whole process of partial eclipse to total eclipse back to partial eclipse can take a few hours. At totality, it's as if it were nighttime. Animals can get confused and start trying to go to sleep. When the moon is blocking the light from the sun, we get to see the sun's corona, so it's a special time for scientific observations. It was also during a total solar eclipse that Sir Arthur Eddington and his teams were able to measure the amount of displacement of a star behind the sun and to thus confirm Einstein's theory of general relativity. Sometimes when the moon is a little bit further away in its orbit, we don't get a total solar eclipse, but we can get just an annular solar eclipse. Annular comes from the Latin word annulus, meaning ring, and so you can see the sun like a ring around the moon. Whenever you're looking at a partial eclipse or an annular eclipse, you need to use eclipse glasses, filters for light from the sun, so that you don't blind yourself. During the few minutes of a total solar eclipse, however, you can remove your eclipse glasses and observe with the naked eye. The total solar eclipse I experienced in 2017 was one of the most spectacular experiences of my life. Earth stands out as the only planet we know of that has life. Why does it have life? What conditions made life possible? One condition is that it has liquid water. In fact, water can exist in its solid, liquid, and gas phases. That's because Earth is at just the right temperature. Its orbit is entirely encompassed in the circumstellar habitable zone. You could think of it as a Goldilocks zone. Not too hot, not too cold, just right. In our solar system, Venus is just inside the habitable zone, and it's experienced a runaway greenhouse effect with its dense atmosphere trapping in all the sun's energy and becoming extremely hot. Mars is inside the circumstellar habitable zone. It can have liquid water. Its atmosphere, however, is not thick enough to preserve liquid water, so it freezes. In the past few years, we've been discovering planets around other stars, and some of those are also in a habitable zone, but we know almost nothing else about them. So this is just a first criterion. Another factor is that our sun happens to be in the galactic habitable zone. It isn't too close to the center of our galaxy, where there's a higher density of stars that could easily disrupt the solar system. And it's not too far out in the galaxy either, where there might not be the right ingredients for a terrestrial planet with all the rich diversity that is necessary for life. Notice also that the sun is in between spiral arms. We know that, and this is an artist's depiction because we don't actually have a picture of the Milky Way from the outside. That would take a long time to get. But we do know it's a spiral galaxy and that the sun is between spiral arms. So we're at a privileged position in our galaxy. Earth is the only planet we know of that has plate tectonics, which are useful for recycling the Earth's surface, keeping it geologically young. Not only is Earth just right for life, but it is also just right for discovery. Our atmosphere is mostly clear. We do have clouds, but there are plenty of days when we have clear skies and we can look out. If we were on the surface of Venus, we would not be able to see through our atmosphere at visible wavelengths. Earth has a strong enough magnetic field to protect us from dangerous radiation from the sun. So many different things had to be just right for there to be life on Earth. Being in the circumstellar habitable zone is one part of it, but that's not enough. Brandon Carter first introduced the Anthropic principle in 1973 as a reaction to the Copernican principle, which states that humans do not occupy a privileged position in the universe. This principle did not come from Copernicus himself, but it takes the idea that Copernicus said we're not in the center of the universe. And so it takes that to mean we're not in a privileged position in the universe. That's not necessarily what Copernicus himself believed, but this principle has come to bear his name. So then the anthropic principle, or anthropic cosmological principle, is a reaction to that. It's saying, well, maybe we are privileged in some sense. After all, Earth has life, and no other planet or moon that we know of has life. John Barrow and Frank Tipler in 1988 wrote a thorough investigation of the anthropic cosmological principle and published this 650-page book. I studied this book as part of my thesis in philosophy when I was at the Pontifical Athenaeum Regina Apostolorum in Rome. In Barrow and Tipler's work, they define certain formulations of the anthropic principle. Here we'll just concern ourselves with the weak and strong formulations. The weak anthropic principle, or WAP, states the observed values of all physical and cosmological quantities are not equally probable, but they take on values restricted by the requirement that there exist sites where carbon-based life can evolve, and by the requirements that the universe be old enough for it to have already done so. In other words, because we're observers, we should expect to see the conditions necessary for life because we're living observers. There's also a strong formulation of the anthropic principle, and it is that the universe must have those properties which allow life to develop within it at some stage in its history. Now, many people today might agree with the weak formulation, but not the strong formulation. And perhaps from a scientific viewpoint, that is what we might conclude. I would say, however, that incorporating faith into it, one would also agree with the strong formulation. This brings us to teleology. Telos was the Greek word for end or purpose. Things happen for a purpose. This has to do with the final cause. Even if we don't know what that end goal is, what that purpose is, we can recognize that there exists one. Different phenomena that hint at that are often called anthropic coincidences. They give us the idea that our universe may be fine-tuned for life. This means that the physical constants in our universe are just right. If gravity were just a little bit stronger, then the universe itself would have stopped expanding a long time ago, contracted, and we would not be here to talk about it. If gravity were just a little bit weaker, then stars and planets would not be able to form. It has to be just right, and it is.